In this ladders question, I'll be showing you how to solve an exam style question, and ideally within the time frame of 9 minutes, as you have 9 marks available. I'm going to draw the diagram again. So we've been given a ladder, and I would recommend that you draw the diagram out as well, just so you can very clearly write down and draw the forces. So this ladder has a length of 2a and the weight is given as w. Before I can put the weight in, I want to find out if the ladder is uniform. So I can quickly scan through the question and try and see if that information is available. And it is. The ladder is modeled as a uniform rod. Therefore, I'm able to put in my force of W newtons. In this particular force, you do not need to worry about weight equals mg. Most students are used to using the maths and writing down mg, but in this question, you've been given W already. So you don't need to be timesing by g. As you can see from Newton's second law, weight is equal to mass times g. So W is already there. The ladder rests in equilibrium with end A on rough horizontal ground and end B against a smooth vertical wall. So I know that my friction is going to be acting against the motion in which the ladder wants to go. The ladder wants to slip towards the left, so my friction is going to be acting against it. And I can write down, because I'm not sure at the moment if this is in limiting equilibrium, I'm just going to write friction there for now. Why did I do that? Because for friction, you could have a situation where you are in equilibrium and you have to consider that friction is less than or equal to mu r. Or if you are in limiting equilibrium, or if you've been told that the ladder is at the point of slipping, then you could and you should write down that friction is at its maximum value, which is mu r, where mu is the coefficient of friction and r is your reaction force. Now, as we've just pointed out r, let's put that in. So there's a contact force at the bottom of the ladder, and that's your reaction force R. And there's also a contact force at the top of the ladder against the wall, and there I'm going to write N. Some people and some students prefer writing R1, R2, or RA, RB, but my preference is to write R here for reaction force and N for normal reaction force. Just going to highlight that this is point A, and this one here is point B. And we've been told that this is rough, that's why I've added the friction. So I've literally put everything I can from the question into my diagram. And this is probably the hardest part when you're trying to answer questions involving static rigid bodies, beams, ladders. So let's carry on reading the question. The ladder rests in a vertical plane perpendicular to the wall and is inclined at an angle theta to the ground. The coefficient of friction between the ladder and the ground is mu. So I've been told that. The ladder is on the point of slipping. So I now know that because the ladder is at the point of slipping, which I've already highlighted beforehand, you can write down your friction as equal to mu r. We are at F max. So instead of just having friction in there, I can equate this to mu r and put that straight into my diagram. So my friction is mu r. The ladder is modeled as a uniform rod, so we've already taken that into account. The mass acts at the center. Show that the coefficient of friction, mu, is equal to 1 over 2 tan theta. Now, for these questions, there is a strategy which you should be using all of the time. And I'm going to be sharing that strategy with you. So the first thing I'd expect you to do is to work out forces up equal forces down. This is very, very simple to do. So forces up, in this case, R is acting upwards, equals forces down, which is W. So you've got your first equation. Following on from here, forces going to the right equal forces going to the left. So the forces going to the right in this case, I'm just going to put in mu r straight away. Mu r against mu r is n. So these are the first two equilibrium conditions that we're going to be using. And this is applied to every question where you're dealing with ladders or rigid bodies in this context. So the next part is what students find difficult, and it is sum of moments clockwise equals sum of moments anti-clockwise. So these are the three conditions that you're going to have to use to answer these types of questions. So let me start taking moments. Most of the time in these questions, you'll be taking moments at A, and the reason for that is because then you can ignore R and the friction force, as there's no distance. If they're trying to take moments at A and the forces act on the pivot at that point A, the distance is zero. Perpendicular distance is zero, therefore you can ignore R and mu r. So taking moments about A, which you can write as M open brackets A close brackets, I'm going to be considering the forces which are acting in this system. So I've got a force of W and I have a force of N. Now you can really consider what's happening in terms of the direction. So if this is my pivot, this force is going to want to move this ladder in a clockwise direction. So you can really think of that beforehand before you actually extract out the triangles. So there's two ways of doing this. Either you can resolve the distance or you can resolve the force. I'm going to start off by showing you how to resolve the distance, and then I will show you another technique that you can use if you want to, where you can resolve the force. So my preference is to take out the triangles. So I'm taking this triangle out. My force is W. Angle here is theta. And I was already told in the beginning of the question that the length of the whole ladder is 2a. Therefore, going to the middle, this length is a, and this length here is also a. Altogether, the full length is 2a. So let me put that length in here. If I resolve this length with this angle, that's my hypotenuse. So this will be a cos theta. Remember, these are the lengths. The black lines represent the lengths. I've resolved the length so I can get a perpendicular distance going from my pivot to my force. And now I'm able to actually work out what the moment is. This is a clockwise moment, and it will be W multiplied by A cos theta. And I'm just going to highlight that this is a clockwise moment. My second force I need to consider is my normal reaction off the wall. Now what you could do is extend this line, extend the force, because that's just representing the direction, and then you should be able to clearly see that there is a triangle which you can form from the pivot and connecting the force. So it will look something like this. This distance is now 2a. Because that's theta, I can use alternate angles and highlight this is theta as well. So let's put that theta in there. And I can now resolve my distance with this angle, and that's the hypotenuse length. So that's going to be 2 sine alpha. I've got my perpendicular distance times by my force, so I can work out my moment. That's going to be N multiplied by 2a sine theta, and this is a anti-clockwise moment. Now, as you can see in my equilibrium condition, that sum of moments clockwise are equal to the sum of moments anti-clockwise. So I will just fill in this equation and write down that WA cos theta is equal to n times 2a sine theta. If you notice, I've got a's on both sides, so I can cancel those out and rewrite this as 2n sine theta is equal to w cos theta. And now you can consider substituting in this equation in for n, or you could actually substitute the n into that equation. Either way, it doesn't really make any difference. But what I'm going to do is I'm going to substitute my r from here, and I'm going to work out what n is and substitute that expression up here. So let's see if that works. N would be equal to w cos theta all divided by 2 sine theta, which equals a half w cot theta. And now I'm going to substitute this value of n in here and this value of r in there and see what happens. So my substitution will be as follows. Mu r equals n. I'm trying to work out what mu is, so let's put that in here. That's going to be n over r. So mu equals n, which I worked out to be a half w cot theta, all divided by r, which I know is w. If I rewrite this, that's the same as saying a half w, let's open this up, that's going to be cos theta over sine theta times by 1 over w, and I can cancel this out, cancel this out. So this leads to mu being equal to 1 over 2 tan theta. And if you're not sure why that's the case, I'll break it down for you. I've managed to get mu is equal to cos theta over 2 sine theta. So from this line, you can see very clearly that I've got cos theta over 2 sine theta because the w's are cancelled out. Now cos theta over sine theta is the same as writing cot theta divided by 2. But cot theta is the same as saying 1 over tan theta. So that's where you can see clearly why this leads to 1 over 2 tan theta.